Hey, I'm sure Starbucks has lots of openings for valedictorians. Okay, so moving on. So like I said, we're going to move away from learning about vectors, guys, in and of themselves, to using vectors as a tool for projectiles. Now, what is a projectile? Well, a projectile is anything that is launched or thrown or shot that moves in a parabola, because the x-axis should have velocity that's constant, and the y-axis should have velocity like an object in free fall. And I have a couple little demonstrations. I'm going to start with this one. This is kind of a fun little deal. It's basically, there's a metal ball in a little plunger, and then there's a spring down below in the plunger, and I have a little pin which holds the plunger in place. Now when I pull the pin, that happens. Okay. So I will show you in a second. It's a very good question. So boop, oh, assuming I don't have the pin in too far. There we go. Okay, that's what happens. So Ryan asked, why is it on a cart? Because it simulates what would happen if you were driving down the road, and in the back of the truck you had your friend with a bowling ball. You're cruising down the freeway, and you throw the bowling ball into the air. Is the bowling ball going to end up back in your lap? Is it going to end up in front of the car? Or is it going to end up on the roof of the car or the hood of the car behind you? Okay, so that's what's basically going on here. So the bowling ball will be emulated by a steel ball, and your friend's muscles will be emulated by a spring. And here we go. So what's going to happen is I'm going to roll this along, and I'm going to pull the pin somewhere along its travel. And you need to figure out, or decide for yourself, will the ball go in front of the car, will the ball go behind the car, or will the ball land back in the tube? So think about it for 10 seconds. Front, back, or tube? Yes. Which is why it's a bowling ball and not a pom-pom. Oh, okay. If you believe, oh, you're discussing it? Okay, I'll give you 5 more seconds. All right. If you think, with a show of hands, if you think the ball is going to go in front of the tube, raise your hand. Nobody. If you believe the ball is going to go back in the tube, raise your hand. About 2/3 of you. And if you believe the ball is going to go behind the tube, raise your hand. About 1/3. Okay, let's check it out. So I'm just going to hold my string right here. What did it do? Right back in. You want to do it again? You're like, it went too fast. Yes. That guy's head was in the way. Okay. So why did it go back in the tube? Ooh, momentum. We haven't even got there. We'll get there in November. But yeah. So as the car was cruising along, what can we say about the velocity of the ball in the tube? Same as the car. So we got launched. Pew! And as it was launching, gravity looked at it and said, oh, I didn't realize you were moving horizontally. Continue on. And gravity said, I'm just going to see you as though you're going up and down. So as far as gravity is concerned, all the ball was doing was going up and down. So gravity didn't play a role in the horizontal direction. As far as gravity was concerned, you just had a ball that went up and back down again. But we know that the ball had horizontal velocity. So when it was launched, it kept that same horizontal velocity. Make sense? Okay. Was there any kind of acceleration in the horizontal direction? No. Because in order to have a constant velocity, you have to have no acceleration. We know there was acceleration in the vertical direction because we gave it an initial velocity and gravity slowed it down and brought it back in. So we know in the horizontal direction there was no acceleration. There was a constant velocity. But in the vertical direction there was acceleration, slowing it down and speeding it back up in. So as long as there was no kind of push to create a horizontal acceleration, the horizontal velocity should be the same. Which makes sense, and that's what it was. Boop, boop. Okay. Are we cool with this? Give me a thumbs up if you have a pretty good idea what happened in here. Okay. Most of you, the people I care about, have their thumbs up. Okay. So let's move on. So now we're going to use vectors not as, we're not going to learn about vectors in and of themselves. We're going to use them as a tool to figure out what's going on in a projectile. And again, a projectile is anything that travels with a parabola. Okay, so two-dimensional motion looks kind of like this. If you were to launch something horizontally, the gravity-free path would just be a green line. If it wasn't launched at all, it would fall, but what really happens is it falls in a parabola. So projectile motion has vertical motion that is simple free fall. Simple free fall, given using the formula y equals 1/2 at squared. dy 1/2 at squared. Vy is just at. Simple free fall. Just like we learned last week and the week before. Simple free fall. Boop.
You seen the basketball video where they throw it off like a dam? Like it goes like straight down and then they spin it and then it flies way out.
Yeah. Oh, what is that called? Starts with an M. But yes. Yeah. Which is why you can throw a ball and it will actually lift as it's traveling towards the plate. Yeah. Horizontal motion, hopefully, with a projectile. Hopefully there is no horizontal acceleration, so horizontal velocity is constant, and the displacement will give us a nice straight curve, or a nice straight line. Yeah, there was a model, I think. I can't remember if it was actually made or if it was just a computer model somebody had of a spherical airplane where its spinning was what kept it aloft. It just kept spinning. Yeah.
And then they like spin the ball, the basketball backwards.
It goes, yeah. Yep. We were just talking about that. It has a name. It has to do with the air friction on a spinning device. Creates kind of a cushion.
It's like a spin on a baseball pitch.
Exactly. Yeah. Which is why you can throw a baseball pitch and it'll climb a little bit as it spins. Okay. So formulas don't change. Okay. The formulas of a projectile, formulas of two-dimensional motion don't change. They are exactly the same as the formulas we use in one-dimensional motion. The difference is we resolve horizontal and vertical motion separately. Okay? And we're going to do a whole bunch of examples. We're going to spend more time on projectiles than we probably should because it's kind of fun. So got projectile motion. Once again, we have x motion and y motion. Both the velocity and displacement and acceleration are represented as vectors. This is a strobe light of what I'm hopefully going to show you. While you take notes, I'm going to show you this. This is something that one of my mentors when I was growing up, when I was actually in grad school, he basically designed this. It's just a piece of wood with a little platform on either end, and I'm going to put a quarter on either side. These are exactly the same quarters, to 2008. There's little grizzly bears on them. They're Alaska quarters. And I'm going to pull them back. I'm going to let it go. The quarter on the back is going to fall straight down. And the quarter on the front is going to get launched horizontally. It's not going to go very far. I'm going to put it over here too. It's going to go like that. So the quarter on, I'm not going to go like, but anyway, the quarter on the back, it looks like this. So here you go, face on. I'm going to pull this back. The quarter on the back is going to fall straight down. The quarter on the front is going to get launched horizontally. Make sense? Okay, so I'm going to pull this back. Whoop. I'm going to let it go. Pew! And the quarter on the front is going to get launched horizontally. And the quarter on the back, because of inertia, that's the object wants to stay at rest. The quarter on the back, the floor is going to fall out, and it's going to fall straight down. So one's going to go whoop, straight down, and one's going to go out like this. Like one quarter is going to be the red ball, one quarter is going to be the yellow ball. Make sense? Okay. Now, while I set that up, I have a question for you. Imagine you took a rifle and you went out to like a really flat area like the Mojave Desert or the Utah Salt Plains, went to a very flat area, and you set your rifle up at exactly 1 meter high. And that rifle, you got a bubble level, and you set that rifle pointing exactly horizontal. You fixed it in position, so there's very little kick. It's going to be like you got a big old tripod or something. Exactly horizontal, 1 meter high. Nothing, you can't see anything but horizon. It's just dirt or dirt. And you shoot your rifle 1 meter high. How long, discuss this with your neighbor while I set the thing up, how long will it take for that bullet to hit the ground? What have you done to your table? Your table's all janky. It's just not allowing this thing to work properly. You broke your table. Okay, well. Yeah, we'll see if that works. Okay, so. Who thinks it might have a number on how long it would take for the bullet to hit the ground? A number. Sure. Less than a second. 0.98 seconds, so just slightly less than a second? Anything else? Interesting. Okay, so we'll revisit that in a second. So here are my quarters. Again, as promised, they're 2008 Alaska quarters with little grizzly bears on them. And I'm going to put them over here. How many clinks are you going to hear? One clink or two clinks? Two clinks. Okay, here we go. Yeah, I know. How many clinks did you hear? One clink. One clink. Even though one went way over here. So we'll try it this time. Maybe it changes if the grizzly bears are pointing up. One clink. Thank you.
What happens if you launch it straight up in the air?
I would have to redesign my apparatus for that. Okay, so how many clinks did you hear? One clink or two clinks? One clink. So even though one was traveling horizontally and it made it like 2 or 3 meters, it still fell at the same rate as the one that just fell straight down. So back to my bullet question. How long does it take for a bullet 1 meter high? This is a yardstick. Meter's about 1 here. How long does it take for a bullet 1 meter high to hit the ground? That long. That long. It takes that long. But Mr. Byers, that bullet would be going really fast. Does gravity care how fast the bullet's moving? No. It really doesn't. So if we want to know how fast it's going, that's chemistry. If we want to know how fast it's going, we just do our d equals 1/2 at squared. So dy equals 1/2 at squared. 1 meter equals 0.5 times 10 times t squared. 0.5 times 10 is usually 5. Yeah. And 1 divided by 5 is usually 0.2. Yeah. So is that about right? So 0.2 equals t squared, or t equals the square root of 0.2. How long does it take? About 0.45 seconds, I think. Did I do a math? Did I?
1 divided by 2. Not.
Oh, 1 divided 0.5. 0.5? Okay. I was right. 0.2.
1 divided by Oh, okay. That's 5. That's 0.5, not 5.
Are you happy with this?
Yes.
Okay. So yeah. So that's the important thing, is it takes the same amount of time as if you just drop the bullet. In fact, if you could create some sort of mechanism where one bullet just fell while the other bullet got shot, they would hit the ground at the same time. I suppose it's entirely possible you could fire a bullet so fast it would follow the curvature of the Earth, but other than that, it's not going to matter. You know, if you fired the bullet at 8,000 kilometers per second, it would follow the curvature of the Earth. But no bullet is actually traveling that fast. 8,000 kilometers per second is really, really, really fast.
They go about 3,300 feet a second.
So, yeah, bullets travel about 500 meters per second. So, in general, about 500 meters per second. So, it's not going to follow the curvature of the Earth. It's going to fall at the same rate. But Mr. Byers, it's traveling so... Gravity doesn't care. Gravity does not care how fast it's traveling. Gravity's going to still pull it down. So the next question is this. If you climbed up to the top of a building and you had an apple, and your neighbor climbed to the top of the building and he had an apple, and one person throws the apple horizontally while at the exact same time the next person drops the apple, are you going to hear splat splat, or are you going to hear splat? Yeah, you're going to hear splat. Because even though one is going out, the other one's falling, they're both going to fall at the same rate. Gravity does not care how fast something is going, because gravity only acts in the vertical direction. So as far as gravity is concerned, whether you drop something or shoot something, you have an object that's traveling in free fall.
No air resistance.
No air resistance, right. We'll deal with air resistance in October, but in September, no air resistance. Sure. But keep in mind, a baseball is designed to have air resistance. If you did it with like if you could do it with like really, really smooth ball to reduce a lot of the air resistance, like a billiard ball. Billiard balls are good for that. Who can tell me, very briefly, why the motion is a parabola and not a straight line?
Object is moving at an exponential rate, and gravity value is so it's moving not inertia.
Okay, so let me just, for Elias's benefit, let me just sum up what's going on over in this corner over here. Yeah, I realize the fantasy football is important, but we got to focus on this too. Okay, so the reason it's a parabola is because gravity is mapping out a distance that is the square of time. Okay, gravity's mapping out a distance which is the square of time. So the distance in the horizontal direction is very, very simple and not written down. It's down here. So the distance in the horizontal direction, dx, is just vx times t. which you can do because velocity doesn't change. Simple. Okay, linear. So this is y equals mx times, or y equals mx, right? It's a linear relationship. However, dy, in dy you have the relationship that maybe you have vyt, but let's go ahead and do at squared to keep it simple. Now you have a situation where you have a t squared. So when one thing changes linearly and the other thing changes with a square, that gives you a parabola.
What is dy? It's like distance?
Yeah, distance how far it falls down.
So you're just putting y in there?
Yep. And that's actually a really good point. Jimmy said you're just putting y up there, and you are just putting y up there because from here on out, guys, from here on out, dx and dy are two very different things. So if you say the displacement is, I want to hear the vertical displacement is or the horizontal displacement is. Because now dx and dy are two very different things.
So dx is horizontal?
Yep, dx is horizontal displacement, dy is vertical displacement.
Sounds like a test question to me.
Using them will be test questions. No, that would be like 8th grade level physical science.
Yes.
You're going to be using dy and dx. All right. Are we feeling comfortable with this stuff?
Yeah.
Give me a thumbs up if you're ready to move on. Okay, looks like about 3/4 of you. I'll take it. Moving on. So, ground launch projectiles. I'll let the animation go first because this is awesome.
Vy, right?
I'm sorry?
Vy?
There is a Vy and Vx too.
Okay. It's like the same thing. Just velocity in that direction.
Straight shoots it.
He's looking.
And he's like 2 points. It doesn't go into the basket, but it does go. Bam! You guys have all played basketball where you air ball and you hit somebody. Yeah. So let that run. Okay. By the way, if you ever find really good physics gifts, I would love if you gave them to me. I usually encounter them just in my general bored wanderings through the internet. But if you ever find some really good physics gifts, yeah, hold on to them. Okay, so ground launch projectiles. Suppose an artillery piece fires a shell from the ground with a velocity of vi and an angle theta. Now, we are going to do a whole bunch of this over and over again. So somewhere around, I think, Thursday, you're going to end up being so bored with ground launch projectiles, you'll want to go outside and shoot some, which is what we're going to do on Friday. So Friday, we're going to take the potato guns outside and fire some potatoes at the construction workers. So we're going to assume the ball starts at ground level. All right. Yeah, I have 2 potato guns. I have a 2-meter potato gun and a 1.5-meter potato gun that you can hold. Then I have a water balloon launcher. We're going to launch them all on Friday. So if you're curious, if you want to launch something out of a potato gun, then you can bring it with you. Yeah. Oh, outside the band room?
Where can I buy a potato?
Can you make a potato gun? Can you buy a potato gun? You can make a potato gun, and you can buy a potato gun on eBay and on the internet. I'm not going to help you build it because I don't want to be party to you breaking windows. But I will tell you this, as a matter of safety, don't use PVC. Okay? PVC is the thick white stuff. When PVC fails, it shatters. Use ABS, which is what I use. ABS is the thick black stuff, it's a little bit softer. It's easier to work with, and when ABS fails, it just warps. So what you don't want is, your friend is like, if this fuel does this, I wonder what this fuel does. And you've never tested it, and your potato gun explodes, and basically you end up in the emergency room with pieces of PVC in your gut. And potato. But mostly PVC. But yeah, so ABS, when it fails, if there's a catastrophic failure, it just warps. It doesn't explode. Like if there's a catastrophic failure in PVC, it shatters. So don't use PVC. I realize it's cheaper, but don't use it. Okay, so moving on. So back to work. Suppose an artillery piece fires a shell from the ground with an angle of v, or angle of theta, and a velocity of vi. What I need from you is, what is that vi and theta? What's vi? Throw a number out. Yeah, it's initial velocity, but throw a number out.
100 meters per second.
100 is even a nice round number. 100 meters per second, about 140 miles per hour. 100 meters per second. And theta, can you see this in the back? Fourth row, can you see the blue? Okay. What is theta? 28 degrees. Okay. All right. So here's the great thing about ground launch projectiles. You're going to have 6 different variables you can calculate. If you have any 2, you have all 6. Okay. So we're launching a projectile at 100 meters per second at 28 degrees. And the first question that we need to answer, actually all of the questions we need to answer, are right here. So can we figure out the final velocity, the flight time, the maximum range, and the maximum height?
Yes.
Yeah, of course we can. So the first thing we need to do is take this velocity, which is not horizontal or vertical, and make it horizontal or vertical. A velocity that is not horizontal or vertical is useless to us. So what we need to do is resolve that velocity into vectors, just like you did in the previous unit. That was an invitation to take out your calculators. Guys, I realize there's lots of love in physics, but keep your hands off each other for a little bit. Well, you're taking it pretty well. Got a very high threshold of pain. No. No. Just like the legs of a right triangle don't add up to its hypotenuse, the Vx and the Vy will not add up to 100.
Okay. Well, I might have
88 for the x or the y? You know what? I'm just going to use 2 significant digits to make it easy. So Vx is going to be 88 meters per second. And what was Vy? 47. Can someone with 2 X chromosomes confirm that? Because we have 3 guys talking. 47? Okay. All right, cool. So can we agree that Y is 47 and X is 88?
Yes, sir.
So this would be equivalent to if somehow you could fire it horizontally at 88 and vertically at 47, which is a simulation we're doing on Friday or Wednesday. Okay, so now we have Vx and Vy, which is great. But we still have a few more things to find. Final velocity, flight time, maximum range, and maximum height. Well, the final velocity is really, really easy. Why is final velocity really, really easy?
It's the ground. All you need is
Exactly. It is exactly the opposite vector of the initial launch. If we ignore air resistance and our VI is 100 meters per second at 28, that means our VF, coming in this way, that means our VF is going to be 100 meters per second at, not 28, but negative 28 degrees. Okay, so again, just like projectiles, just like things that go up and come down, projectiles also go up and come down at the exact same rate, but their vectors are inverted. So if something goes this way at 100 meters per second, it comes that way at 100 meters per second, ignoring air resistance. And I got a really cool lab for you in October where Angry Bird. Yeah, we could use Angry Birds. We can use Angry Birds, sure. We're going to play Angry Birds. We're going to play Angry Birds and Angry Pom-Poms. We're basically what we're going to do is we're going to launch things that have very little air resistance. Then we're going to launch things that have lots of air resistance, like a cuddly little Angry Bird or a pom-pom. Okay, so that's done. Final velocity, Piece of cake. Flight time. Can we come up with flight time?
We should be able to.
We really can. So let me walk you through this system. If you launch something upward at 10 meters per second, how long until it stops moving? 1 second. Because gravity slows things down at 10. So if you launch something up at 10, it stops in 1 second. If you launch something up at 20, how long does it take to stop? 2 seconds. If you launch something up at 30, how long does it take to stop? 3 seconds. If you launch something up at 47, how long does it take to stop? 4.7 seconds. Okay, so time top is 4.7 seconds. How'd you get that? All I did is take Vy and divide it by 10. Because you told me that if something goes up at 30 meters per second, it takes 3 seconds to stop. And if something goes up at 40 meters per second, it takes 4 seconds to stop. So if something goes up at 47, it takes 4.7 seconds to stop. Make sense? So if it takes 4.7 seconds to go up, how long does it take to go back down? 4.7 seconds. So our total time, and our black pen is disappeared over here. Our total time is that multiplied by 2, 9.4. Pretend that's a 4. Okay, 9.4 seconds.
So will that work every time? Just Vy divided by 2?
Yep. Good question. Will that work every time? Absolutely, it will that work every time, because we are not going to do projectiles with air resistance. We're going to investigate air resistance by itself when we talk about forces, but we're not going to use air resistance for anything in projectiles. Does that make sense? Not even the AP is that cruel. They won't even do air resistance when you're doing the AP test. If there's a projectile, they'll be like, no air resistance. We're going to investigate air resistance in and of itself when we do forces. Okay, does that make sense? Give me a thumbs up if this makes sense to you. Why 9.4? Not a lot of you. Okay, let's go over again. So the Vy is 47 meters per second. It is as though we launched it straight up at 47 meters per second. 1 second later, it was traveling at 37. 2 seconds later, it was traveling at 27, then 17, then 7, then 0. Gravity pulled it down at negative 10 meters per second, slowing it down to a stop in 4.7 seconds. Okay, thumbs up there if that makes sense to you. Okay, if it stopped in 4.7 seconds, that means it took 4.7 seconds to go up and 4.7 seconds to come back down, for a grand total of 9.4 seconds. That's where I got that number. Are we cool? Okay, so that's our total flight time, and we checked a box. Okay. Maximum range. So in other words, the range from here to here, dx. How might I find maximum range? I'll give you a hint. It's written on the board. Yes?
Why did time has to be multiplied by 2?
Because it takes half the time to come up, half the time to come back down. So it took 4.7 seconds to get to our top and 4.7 seconds to come back down. Okay, and I heard some whispering about what formula do I use? What formula do I use?
Dx equals Vx times.
Excellent. Dx equals Vx times t. Our Vx is our 88 meters per second. And our time is whatever time we want to use. You can find out how far it's gone at any point in this time just by plugging time in. Okay. But we care about how the maximum range. So the maximum range is what time? 9.4. Again, you can plug whatever time you want in here to find out how far it goes. You can find out how far it's gone in 1 second, 2 seconds, 3 seconds. You can find out how far it's gone at the highest point. You can find out how far it's gone in 5 seconds, 6 seconds, 7 seconds, 8 seconds, 9 seconds, or whatever. But if you want to know the maximum range, it's when it comes back to the ground at 9.4 seconds. How far is that?
827.2 seconds.
827? I'm just going to round that to 830. meters. No, that's significant digits. I'm gonna stick with two significant. You gave me 28 degrees. You didn't say 28.0 degrees, so I'm gonna go with two significant digits. Although you did give me 100, so maybe I should use one, but no. Okay. Okay. So to find range, all you need to know is how fast is your Vx and how long is it in the air. But you can find out how far it goes at any point in there. Okay, cool? And we're done with dx. Last thing, dy, maximum height. And this is where things get a little dicey. Maximum height can be done twice, or two different ways. I'm going to show you how to do the easy way and the less easy way, because you need to know both. Okay. Yes.
Free-fall formula?
Exactly, yeah. The maximum height is the free fall formula. dy equals 1/2 at squared. In other words, it is, if something fell for 4.7 seconds, you know the height from which it fell. If something fell for any amount of time, you know the height from which it fell. So if you know the height from which it fell, you know the height it got to. It unfell to? Okay. So what is the maximum height? No, the time at the top is 4.7. 110? Okay, so somebody banged on their calculator and they did 1/2 at squared using 0.5 times 10 times 4.7 times 4.7?
Yep.
Okay. So if you only care about the maximum height, then you just do d equals 1/2 at squared, because that is the height from which it fell. And if you know the height from which it fell, you know the height to which it unfell. She's like, whoa, brain, boom. But okay. So it got to a height of 110 meters.
Is the time thing a coincidence that there's a gravitational constant, or is that kind of
What time is
Oh, yeah, it's not just it's 9.8, but it would be a coincidence if it happened to be. If you gave me like 4.9 and 9.8 seconds, it would still be a coincidence. Yeah. Okay, does this idea make sense? Now, though, using the free fall formula, d equals 1/2 at squared, is useful if you want to know the maximum height. But if you want to know the height anywhere, we have to add a term. Okay, so that's dy max. But if you want to know the height anywhere, dy equals vyt plus 1/2 at squared. If you want to know the height at any point in time, that's the formula you use. Yes. Like I said a half hour ago, it's exactly the same formulas from the last unit. It's just we have to resolve the x and the y independently of each other. So 1/2 at squared is useful if you just want to know the max. But if you want to know the height at any point in time, dy equals dyt plus 1/2 at squared. So let's do that. Okay. So I want to make sure we're cool with this before we move on. Okay, what I'd like you to know, or I'd like you to tell me, is if let's put a building right here. Okay, it's a Waberly building, and there's Jimmy in the window, and someone's like, "Let's hit Jimmy's building," it turns out the projectile is going to hit Jimmy's building at time equals 8 seconds. This is going on YouTube, dude. You're gonna have a visit. Okay, so there's Jimmy, and Jimmy he gets hit by the projectile, or he catches it. The projectile is just like, he's like, ooh, whoosh, and he catches it at 8 seconds. I want to know how far he was from the cannon and how high he was. You have 7 minutes.
I can tell you how high it was
because he was there. Yeah, I was there. Yeah. So using the formulas that you now have, in 8 seconds, the projectile hits Jimmy's window. How high was Jimmy's window, and how far from the cannon was it?
game stuff in right now.